The method that I'm going to suggest to you is very specific, and the steps are clearly outlined here. The first step is we start with a molecular formula, and we try to figure out the atom with the lowest electronegativity, and we put that, once we find it, in the center. The exception is hydrogen. We don't put hydrogen in the center. But other atoms, we compare them according to electronegativity trends, like we saw before, and we place that atom in the center. Now, once we have that topology, really it's the topology of the molecule. Once we have the topology, then the next thing to do is to figure out how many total valence electrons there are available for the atoms in this molecule. So we add them up. Okay? We're not going to be doing this for, at least not much, for transition metals. It'll all be main group for the most part. And so we add up the group numbers and we count the electrons that way. Once we have the sum of the valence electrons, the number, then we draw single bonds from that center atom to all of the outside atoms. And we subtract 2 electrons for each one of the bonds that we make that way from the sum of the valence. Then we take the remaining valence electrons and we put them around the outside atoms to make octets, or in the case of hydrogen, make duets. And if there are any atoms left, any electrons left over after we've made all those octets, they go on the center atom. Okay, so those are the steps, and I want to just take you through a molecule and an ion and a few other cases. Let's suppose the molecule we want to do is nitrogen trifluoride. Now, for such a molecule, we inspect the molecule, which might be given in general terms as A, B taken n times, and we try to find out which one of the atoms present has the lowest electronegativity. And in the case of NF3, this is pretty obvious. If we compare nitrogen's position in the table here to fluorine's position over here, it's 2 steps to the right, so fluorine has a higher electronegativity, and nitrogen should be the centered atom. Okay? So what we do then is write nitrogen in the center and write the fluorines around it like this. Now, we are not doing the geometric structure at this point. The only structural feature we have is something is centered and everything else is around it. So it's not hard. It's easy. So at this point, we are ready for the next step, which is to add up the valence electrons for a nitrogen and 3 fluorines. And nitrogen is group 5, so it has 5 valence electrons. And each fluorine, being in group 7, has 7. So it's 5 plus 3 times 7. 5 plus 21 is 26 total valence electrons for this molecule. We don't do core. We're only interested in the valence because it's the valence that determines the structure. And so we take these 26 electrons and we start off very simply by drawing single bonds from the nitrogen to each one of the fluorines. Now, in case this had been a polyatomic cation or anion, we would have made an adjustment in the total valence electrons for the charge. And I forgot to mention it here. If we have a negatively charged polyatomic ion with one, if it has one negative charge, we add 1 electron, which is the source of that charge. If it's a positive charge, then we subtract 1 electron in order to produce the positive charge. So we don't have a polyatomic ion this time, but we will soon. So let's look at this molecule and its 26 electrons. So we draw a single bond from the nitrogen to the fluorine 3 times. And then we subtract 2 valence electrons for each one of these bonds. Okay? They are now used up, and we get them out of the total. So 3 NF bonds times 2 electrons per single bond gives us 6 electrons that are used up. So 26 minus 6 gives us 20 electrons remaining. Once we have done that and made those single bonds using this method, we distribute the remaining electrons in pairs so that each atom shares 8 electrons. Each atom has an octet. That's what we're talking about here, except 2 for hydrogen, of course. So we have 20 electrons, and we're going to distribute them so that this fluorine has an octet. It has 2 electrons now, so it needs 6 more, and it's going to get those 6 in 3 sets of 2. And then we'll do the same thing for this fluorine and this fluorine. Okay? And we don't do anything with the nitrogen until we're done with the fluorines. Okay. So I think you can see from this that each nitrogen, each fluorine consumes 6 electrons. So that's 6. 6 more is 12. 6 more is 18. So then we have 20 electrons that we started with, minus 18 electrons, and that leaves 2 electrons left over. And all of the 3 fluorines have an octet, so we can't put any more electrons around them. You don't want to exceed an octet for a small atom like fluorine, so you end up putting those 2 electrons on nitrogen. Okay, so here's how it goes. 2, 4, 6, 8, 10, 12, 14, 16, 18, and then 2 more in the middle. Now we have to inspect for an octet to see whether we did this right, and we will look at each one of the fluorines. All 3 fluorines. Whoops, went one too far. So. Okay, all 3 fluorines have the octet. The nitrogen has the octet, and it's good practice to just draw a circle around the 8 electrons, so you're sure about it. Okay, 1, 2, 3, 4. So the electrons are now arranged so that we have an octet for all 4 of the atoms. That's the most stable electron configuration for a molecule like this. Okay, so that's how you get the electron dot diagram for NF3. Does anybody have a question about it? Okay. I'm going to continue and then do an ion for you. And the ion I would like to do is a polyatomic anion called the tetrafluoroborate ion, BF4 minus. Now, as you think about the periodic table, boron is, of course, well to the left of fluorine. Therefore, its electronegativity is a lot less than fluorine, and it should be the center atom. Okay, so we decide on the topology. We put boron in the middle because its electronegativity is smaller, and the arrangement of the fluorines around it is arbitrary at this point. I've just written them around there, and I'm not trying to specify what the geometric structure is or anything. I'm just saying boron's in the middle, fluorines are on the outside. So having done that, then it's time to determine the total number of valence electrons. Boron is in group 3A, so it has 3. Each fluorine has 7, as we saw before, and now there are 4 fluorines, so that's 28. And there's 1 negative charge here. 1 negative charge, so we add 1 electron for the negative charge. And if I counted them up right, that should be 32 electrons. So what we're going to do next is to take those 32 electrons and make 4 single bonds. And here are the 4 single BF bonds. And we're going to subtract 2 electrons for each one of those 4 bonds. And so that will mean 8 electrons were consumed making those bonds. And the 32 that we started with is now less by 8. So there's 24 electrons remaining. And as you recall, we will use those electrons to make octets for the outer atoms first. So here they are. Each one of the fluorines has 6. There are 4 fluorines. That's 24. And that's all the electrons that we have. And that's a good thing because boron, having 4 bonds around it, already has an octet. It doesn't need any more electrons. And fortunately, there aren't any to give it. So that's BF4 minus. Notice that since it's an ion, I draw brackets around the ion, and I put its charge outside. So we'll know that it has that one negative charge. Does anybody have a question on tetrafluoroborate ion? Okay, good, good. Let's go ahead and look at cases where there might be more than one center atom and see what the rules are there. Well, I'll jump the gun and just tell you that if there's more than one center atom, we treat each one as a center atom. And we add 1 bond between them and see what happens. So the molecule I want to talk to you about is methyl alcohol, sometimes called methanol, sometimes called wood alcohol, sometimes called an industrial alcohol. Its formula is CH3OH. And so there are 2 heavy atoms. Remembering that hydrogen can never be a center atom, the center atoms in this case will be the other 2 atoms, which are carbon and oxygen. And so we would set up a topology with carbon and oxygen as the center atoms. And here they are. And now I need one additional piece of information to get started properly here, and that is some notion of how many bonds each one of the center atoms will form. And we've been there before. We visited that place a while back. We already know that carbon forms how many bonds? 4, almost always 4 bonds. And oxygen forms 2 or maybe 3. Okay, so I distribute the hydrogens so that once we have a bond between the carbon and the oxygen, I have enough hydrogens to make 3 other bonds to total up 4 for carbon. That carbon will be a happy carbon. Okay? And oxygen is set up so that after the bond from carbon to it, there will be 1 more hydrogen to give it 2 bonds. Well, let's see what that produces here. We're going to find the sum of the valence electrons. Carbon has 4, oxygen has 6, each hydrogen has 1. That will give us 14 electrons. And then we can take those 14 electrons and start to make single bonds between the center atoms and between each one of the center atoms and the outer atoms. Okay? It's very easy to do. No way to make a mistake here. 1 CH, 2 CH, 3 CH, 1 CO, and 1 OH. 5 bonds, 1, 2, 3, 4, 5. Subtract 2 electrons from each. So we started with 14. That's 5 times 2 is 10 electrons. There are 4 electrons left. And we use those 4 electrons to try to achieve an octet or a duet as needed. Well, now the carbon already has 8 electrons. It has an octet, so we don't have to do anything for it. And every one of the hydrogens has a 2-electron bond, so they are in good condition. We don't need to change anything. But oxygen only has 4 electrons around it, so we use the 2 electrons as 2 lone pairs around the oxygen, as you can see. Now the oxygen has 8 electrons, the carbon has 8 electrons, and each one of the hydrogens has 2 electrons, and we are where we want to be, right? Carbon has an octet, the oxygen has an octet. Do we have questions on that? None? You know it already. Good. Good. All right. Now we talked, was it Monday? I think it was last Friday, about multiple bonds. So let's look at some examples where single bonds just won't do the job. And we have to make multiple bonds. Let's see how to do that, because that's one of the trickier places for drawing Lewis dot structures. And I want to be sure you're comfortable with it. So what will happen is that sometimes you'll go through those 4 steps that we just did for those molecules, 3 molecules, and there may not be enough electrons so that the central atom or atoms have an octet. So if you get to step 4 and you haven't completed the octet for everybody, you may need to make a multiple bond. And in fact, making a multiple bond is a usual way to get around that problem of less than an octet for some atoms here. So if that's the case, we're going to do it an additional step, and the additional step is step 5. If the central atom lacks an octet, use a lone pair from an adjacent atom to make a multiple bond. So that instead of 2 electrons being shared, a single bond, we make 4 electrons be shared, and that would be a double bond. So I'm going to write the Lewis structures for 2 examples, one of which has a double bond and one of which has a triple bond. Let's start with ethylene. If you go through the process for ethylene, you put the 2 carbon atoms in the middle. You put the hydrogens 2 on each carbon, since we only have 4 to work with. And you follow you count the electrons. There's 8 and 4 is 12 electrons. You follow it through. By the time you get to the last step 4, you have a 1 pair of electrons that is earmarked for either of the center atoms here. But you don't have enough for each one of them to have the pair of electrons. So you get something that looks either like this or with this pair on this carbon over here. Well, this carbon's fine. It's got 8 electrons. But this carbon has 6 electrons. You cannot leave a carbon with 6 electrons. It will need psychiatric help after a short period of time if you do that. It expects 8 electrons, and it's up to you to get it. Besides that, if you take organic chemistry and you leave a carbon with 6 electrons around it, you'll earn a very large red mark, okay, on your test. All right, so what the process says is after step 4, you don't have an octet for everybody. You need to use a lone pair on an adjacent atom to create a double bond. So that's what we're going to do. We have this lone pair here, and we're going to convert it into the second bond of a double bond. We're going to take that pair of electrons and put it over there with a, this is right out of organic chemistry. They use arrows to move pairs of electrons around. So we're moving this electron into the region between the 2 carbons. And when we've done that, then we have 4 electrons shared, and each carbon now has an octet. And so making a multiple bond gets us 2 carbon atoms in the condition that they need to be in. Only doing that gets you to that place. Otherwise, you're going to have 1 carbon which is not where it needs to be in all cases. Questions on C2H4? We said a while back that C2H4 had a double bond, but at the time I said I'm not going to show you how it got a double bond until later. We're there. This is later. Okay, what about N2? If you start through the process of drawing a Lewis dot structure for dinitrogen, you have 10 electrons to work with. Maybe we should just go through it so the people who are talking will hear it. we'll draw the two nitrogens, and we'll count the electrons. 2 times 5 is 10 electrons, right? So we'll put in a double bond, a single bond between the two atoms, not a double bond, a single bond, and we'll subtract 2 electrons from the 10, and we've got 8. And then we'll put the 8 separately on the 2 center atoms. The 2 nitrogens is all the atoms we've got. Okay? So after step 4, this is what we have. Does either nitrogen have an octet? Does not. Neither one does. 2, 4, 6, 2, 4, 6. The double bond counts for both of them. I mean, the 2 electrons in the single bond count for both. But in order to achieve an octet for both nitrogens, we have to go through the same process we talked about before. We take a lone pair and we use it to make an additional bond. So let's just say we'll pick this one. We could have picked this one over here, or this one, or that one. It doesn't matter. We'll take that pair of electrons and we'll make a double bond. And here's what it looks like when we're done. Now the nitrogen on the left is smiling. I'm sure you can see that. It has 2, 4, 6, 8 electrons around it, and no problems there. But this nitrogen here has a severe headache. It only has 6 electrons, and it can't stay that way. So we're not done yet. We have to keep going until everybody has an octet who needs one. So we're going to take another pair of electrons, this time from the other atom, and put it in and make a triple bond. And when we do that, then each nitrogen has 8 electrons, 2, 4, 6, 8, 2, 4, 6, 8. And in N2, the only way you can get an octet is to make a triple bond. So that's how you, 1, determine that a multiple bond is necessary, and 2, find out whether it needs to be a double bond or it needs to be a triple bond. Do you have questions? Okay. Yes, go ahead.
Is a triple bond the most we're going to see, or maybe more than that?
There are quadruple bonds, but their explanation lies beyond the foundation that we've built for ourselves here. They are in the D block, and the electron configuration of the D block requires more tools than we have in our toolbox at the moment. Okay? All right. Now, let's do this. There is a chemical substance known as phosgene. And if you've ever been in a small town with a railroad crossing around here, particularly down towards Freeport, and a train came by with tank cars, it is quite likely that you'll see that at least one of the tank cars says phosgene on it. And my son always wanted to know, the older son, always wanted to know what the formula for phosgene was, whether it had phosphorus in it or not. Okay? And of course it doesn't. It's not a phosphorus compound. Its formula is COCl2, and this problem asks us to write a plausible Lewis structure for it. Now, the initial approach to this ought to be to figure out, since we have 4 atoms, which one is the center atom. And if you look at the electronegativity of carbon, oxygen, and chlorine, which one is lowest? Carbon, oxygen, and chlorine. Carbon is. Carbon is lowest, so let's put carbon in the middle. All right? Whoops. Sorry. We're going to put carbon in the middle, and we'll put oxygen over here, and chlorine over here, and chlorine over there. Okay? That looks like a decent topology. I'm not saying this is the structure. I'm just saying carbon is likely to be the atom in the middle. Now, if I once I have determined that, if I count the electrons, carbon has 4, oxygen has 6 valence electrons, and chlorines have 7, and there are 2 of them. So 2 times 7 is 14. It looks like 24 electrons. Right? Now, let's take 2, 4, 6 of those electrons and make single bonds between the carbon and the 2 chlorines and the oxygen. So 24 minus 6 looks like 18. 18 electrons to work with. All right, so we'll put them around the outer atoms in pairs of 2. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, and 18 minus 18 is 0, and there aren't any electrons left. But can we stop here? No. We cannot, and I guess you could see the reason why. This carbon has only 6 electrons around it. Now, as you think about this, we now enter a gray area, because we could conceivably take a chlorine lone pair and make a carbon-chlorine double bond, or we could take an oxygen lone pair and make an oxygen-carbon double bond. The choice about that is based on what we already know about the covalent bond preferences of some of these atoms. Chlorine, as an HCl, forms typically 1 covalent bond. So it might not make sense for us to make a carbon-chlorine double bond. On the other hand, oxygen likes 2 bonds, typically, and we could anticipate that and take a lone pair of electrons from the oxygen. And if we did that, we would make a double bond between oxygen and carbon. And keep our carbon-chlorine single bonds, both of them. And now let's count electrons. 2, 4, 6, 8. So there's an octet there. 2, 4, 6, 8. An octet there. An octet here, not including these up here. And an octet here. So now we have the Lewis dot structure for phosgene. It has 1 multiple bond, which is a double bond, and it has 2 single bonds. And if the question asked how many lone pairs are there in the structure of phosgene, this is how you would find out. You would draw the proper Lewis dot structure and count them. 1, 2, 3, 4, 5, 6, 7, 8. Let's go back to ozone. And if you remember, in the case of ozone, we had a oxygen-oxygen single bond and an oxygen-oxygen double bond that were adjacent to one another. And there were 2 ways that that could be written depending on which external oxygen you picked. I'll wait until you ladies are done. Thank you. If I pick the left-hand oxygen to use a lone pair from to make the double bond, then we'll get a structure like 1 here. If I pick the right-hand one, like I did in drawing this out initially, then I'll get a double bond over here, and it'll look like 2. And what I said before is that neither one of these 2 Lewis dot structures, both of which are octet OK, neither one correctly represents ozone, because, as I said, experimentally the ozone bonds are identical. Okay, the molecule has equal oxygen-oxygen bond lengths and bond strengths. So we cannot choose either one of these to describe it by itself, because each one would suggest that one of the oxygens is shorter and stronger than the other. One of the oxygen-oxygen bonds is shorter and stronger. So we can't do this. So the valence bond model has an extra step, one more extra step, to deal with this problem. And it works like this. If you have a Lewis dot structure that has a single bond adjacent to a double or a triple bond, that is said to be a special state which requires something called resonance. And resonance is a peculiar wave mechanical process that describes what's called delocalization of electrons, meaning we no longer look at the electrons, all of the electrons in the molecule, as if they were nailed down in place. Some of them, in the resonance description, will be free to move. Okay? So, when we have this kind of a situation, a single bond adjacent to a double bond, we draw both possibilities. And we draw between them a double-headed resonance arrow. You'll get a number of questions of the form, which of the following species exhibits resonance? The criterion you use to answer the question is, does it have a single bond adjacent to a multiple bond? If it does, it will, in all likelihood, exhibit resonance as the best way the valence bond model can describe this. Now, later we're going to talk about the molecular orbital model, which is a much more high-level model, and it, by itself, describes the bonding in ozone as a delocalized bonding case. You don't have to add in any special parts like showing resonance. But resonance is okay. It's easy enough to see when to expect it. And you notice here these arrows. These are electron-pushing arrows that the organic chemists just love. So if you're going to take organic chemistry, you'll see a bunch of these. And all this says is to get from this form over to that form, you can push a lone pair from the right-hand oxygen and make a double bond here. And at the same time you do that, you have to push a pair of electrons from the double bond on this side over to make a lone pair. If you don't do the second step, then this oxygen has 10 electrons around it, and a red light goes on, and you know, the three big guys come around and say, don't you know you can't exceed the octet for oxygen? All right. So resonance structures are described as having the same sequence of atoms, O, 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 but different locations for the electron pairs. All right. Now, what I would like to do is to show you how to represent the molecule of ozone other than writing these two resonance forms. These are resonance forms. What we do is we take the idea developed in these resonance forms and condense it down into something called the resonance hybrid, which is something like an average of these two forms. It's a melding of the two. And I have drawn the picture of it here. This happens to be a hard one because there are two pairs of electrons that are involved in the resonance hybrid, and they are mobile. One pair of them has to do with a lone pair operation. It's a lone pair type of electron. And the other one is a bonding pair type of electron. Now, all we need to do to really describe this is to draw this dotted line from the left-hand oxygen over to the right-hand oxygen. That dotted line means there's one pair of electrons, let's say that one right there, which can be here and it can be over there. Now, I don't mean to imply that it jumps back and forth. That's not what happens. What happens is, in the wave mechanical description of this, this pair of electrons is smeared out between those two bonds. Okay? So if you took a snapshot of the atom, it would not look like this one time and that another time. It wouldn't look like either one of those. It would look like something like this. There would be a blurry pair of electrons spread out like a fog across here. Now, this is an interesting idea. It's not an easy idea to absorb, but if you look at this, if you look at these bonds, the one pair of electrons in this resonance hybrid is localized between these two oxygens, and the other pair of electrons is spread out so that it occupies this, what would have been a double bond, not part of the time, but in part, meaning a fraction of the electron pair is always here, and a fraction is over here. So this says the oxygen-oxygen bond order is between 1 and 2. And we could see that more easily up here, actually. There is a single bond, bond order 1, and a double bond, bond order 2. So if you average these two, like we said for the hybrid, it's going to come out 1.5. Okay, so now you've seen how to detect when there's resonance, how to write the resonance forms, how to write the resonance hybrid, and you've seen, maybe for the first time, how to write the bond order of the bonds in the resonance hybrid. Okay? Questions on that up to this point? Yes?
Okay. Would that be possible for, let's say, a double and a triple bond sequence?
He asked if it would be, if something like this, if you had a double bond and a triple bond here, would it be possible to write a hybrid between them? Yes. In fact, I'm going to show you an example in a little bit that has something like that. Okay. You have to keep in mind you can't exceed the octet. So the extent that we can do what you ask is partially dictated by that. All right, so in the ozone resonance hybrid, two pairs of electrons are delocalized. One has to do with it spending some of its time as a lone pair here and a lone pair here, and the other one is a pair of electrons that spends its existence is spread out between these two bonds. So what happens here is, if that's true, if that wandering pair of electrons in the middle here spends half its time here and half its time there, that'll make these two bonds completely equivalent, right? And each one of them will consist of a single bond, a localized electron pair, and a partial bond, which is a delocalized electron pair. Okay? Now, here are the two bonds, and imagine that over here, each one of them is the average of these two. Now, delocalization is an interesting concept because it takes localized negative charge and spreads it out. Well, among other things, that lowers electron-electron repulsion, Coulomb's law. Ma'am, would you please close your laptop? I'm sorry, I asked you to bring your notes on paper. You can leave it open now, but in the future, please bring paper. I think it's better. All right, so delocalization reduces electron-electron pair repulsions. Now, what about the bond order? If we think about, just pick one of these resonance forms and think about what the bond order could be. Well, the bond order is the number of electron pairs divided by the number of links between the atoms. I'm tempted to say bonds, but that might be misleading. So if we look at one of these, we have 1, 2, 3 pairs of electrons. These are bonding electrons. Bonding E minus, divided by 2 links, 2 oxygen-oxygen links. So the bond order for this delocalized case is 1.5, 1.5. 1.5. And what's neat about this and why it's worth buying into is if you go to a table of bond lengths and bond energies and you look up an oxygen-oxygen single bond and an oxygen-oxygen double bond and you compare that to the bond lengths for ozone, what you see is it's halfway in between the two. So it works. It might be a little stretch, but it does work. All right. Now I'd like to look at a couple other cases of resonance because in the past I got lots of questions about resonance. Any questions here so far? All right. In the carbonate ion, CO3 2-, there are 24 electrons. And when you put carbon in the middle, and the 3 oxygens around the outside, and remember this is a dinegative ion, you have your 24 electrons, and you draw 3 single bonds. So 24 electrons minus 6 is 18 electrons. Then you put the 18 electrons on the oxygens. That's 6. That's 12. That's 18. So we have now used all of the electrons. There are none left. But the carbon doesn't have an octet. So we got to go ahead and give carbon an octet. And now we have 3 different ways that we could give carbon an octet. We could make a double bond from this oxygen at 2 o'clock, one at 4 o'clock, or the one at 9 o'clock. Right? If I pick this one and make a double bond right there, I get this structure. Carbon-oxygen double bond, 2 lone pairs, 2 carbon-oxygen single bonds. Now, I think you can see, I won't draw the whole thing here, but I think you can see there are 3 different ways to do this with respect to where you put the carbon-oxygen double bond. And those are the backbones of them. Now, when you ask yourself what would the bond order for these carbon-oxygen bonds be in case somebody asked you to predict the bond length or the bond energy, which somebody might. Wouldn't be me, but somebody might. You should look at this and see that there are 4 bonding electron pairs. And those 4 electron pairs are spread over 1, 2, 3 links. And so that will leave a bond order of 1.33. So this suggests that the bonds in carbonate, in the carbonate ion, ought to be about 1 1/3 times stronger than carbon-oxygen single bonds. And they ought to have a length corresponding to 1/3 of the way from a single bond down to a double bond, roughly. Yes, go ahead.
Okay, so when you say bonding pairs, that's
That one, that one, that one, that one. Well, these are the only bonding pairs of electrons that I've marked here. The rest are lone pairs. Okay. Now, if somebody asked you, what does the resonance hybrid look like for carbonate ion, what would you do? First, you draw the backbone, and then you draw dotted lines to represent the delocalized pair of electrons that makes the 4th one here. And at this ion, the delocalization goes out over 3 different bonds. So 1 pair of electrons smeared over 3 links. Question?
If you were trying to signify that there were 2 bonds being shared between the 3 oxygens, would you have 2 double
he asked if you had two delocalized pairs of electrons, how could you represent them? And what you would have to do in that case is draw all of the possible ways you could take, let's suppose this were a sulfur, for example, or some other element, and this was a double bond and that was a double bond. Then you would write all of the other possible ways to write two double bonds. One here and a single bond there. One here and a single bond there. Whatever others seem to be needed.
But as the resonance hybrid.
As a resonance hybrid, you don't distinguish the total number of delocalized bonds in terms of the dotted line. You don't put two dotted lines or something like that. You would just show where the electron delocalization occurred and write under it or something that there were two pairs delocalized. This happens in the sulfate ion. Yes?
Could you go ahead and put down the electrons in the hybrid?
No, you can't.
So you don't.
Frequently, it is not possible to write, using the resonance thing, a proper representation of the Lewis dot structure. It just doesn't work. And it's a drawback for this method. But what we need to focus on is the bonding part of it anyhow. And it does an adequate job there. Mm-hmm.
But so for with oxygen 3, we showed the electrons.
Yeah.
So that's not necessarily correct.
But we didn't do it well.
So
Way back when this textbook started, the author had, remember I told you that Silverberg he's an author, he's not a chemist. He had a lot of trouble with this and wrote letters to many people who were involved in this about what was the real proper way to do it. And he made a choice about how to do it that most chemists probably don't agree with. But he felt it was important to convey a whole Lewis dot structure. And unfortunately, that just does not always work. And in the case of ozone, you have a lone pair resonating, which isn't represented in his structure. Okay? So that's the problem with it.
So in the resonance hybrid model, we should not put down the free electrons?
If somebody asks you to draw or sketch the resonance hybrid, just sketch the bonding part of it. Don't put in any electrons. Questions? 3 carbon-oxygen bonds are the 3 links I was talking about. I'm sorry, I don't understand your question. Could you speak a little louder? Okay, thank you. All right, what about the nitrate ion? Well, the nitrate ion is also an example of an oxoanion that exhibits resonance, and it happens that NO3 minus has exactly the same number of electrons as CO3 2 minus. And up to and through step 4, what you have for the nitrate ion looks like this. A nitrogen with 3 single bonds, but the nitrogen lacks what? It lacks an octet. Thank you very much. So we need to change one lone pair on one of the oxygens to a bonding pair. And when we do that, if you have a question, please ask it to me. Okay? I'm going to wait until it gets quiet. If I don't cover everything, you can blame it on the people who insist on talking. Thank you. Okay. So nitrate is, in many respects, very much like carbonate because it has the same number of electrons. It's isoelectronic with carbonate. So lacking an octet around the nitrogen, the lone pair of one of the oxygens is used to make a double bond and an octet. Okay, so one of the possible resonance forms for nitrate ion looks like this. And I know there are other resonance forms because I have single bond adjacent to a double bond. Right? And I think you can easily show that the double bond could be here, or it could be over here. So you should have 3 resonance forms, and here they are. All that we need to do then is to try to represent the resonance hybrid. And again, I suggest that you don't worry about the lone pairs. We have 1 pair of electrons that is delocalized for bonding over 3 links here. So the easiest way to draw that is to put it dotted lines like that, like that. The bond order is 1, 2, 3, 4 bonding pairs. Yeah, I do. Thank you. I need to always remember to put the charge up there, or my number of electrons will be wrong. Okay? So now we have 4 bonding pairs. And we have 3 links. NO, NO, NO. Those are the links. And so the bond order will be 1.33, just like it was in carbonate. So in symmetrical structures like ozone, the resonance forms are equally mixed to form the hybrid, as we saw. But when we don't have symmetrical structures, then one resonance form may contribute more to the hybrid than the others. And we need a tool to help us tell which one that will be, because the properties of the molecule are indicated by the properties of the hybrid, not the resonance forms individually, but the properties of the hybrid. And so we need to be able to describe the hybrid if it's not symmetrical. And we have a way to do this. This is Electron Bookkeeping 101. It's called formal charge, abbreviated by me, FC. The equation for it is simple. The formal charge of an atom is equal to the number of valence electrons the atom has as an atom minus the number of unshared valence electrons it has in the molecule or ion minus 1/2 of the shared valence electrons. So minus the lone pair electrons minus 1/2 of the bonding pair electrons. That's what this says. The formal charge works like this. Back in Chapter 8, we talked about 2 things of interest here. First, ionization energy. If we take an electron away from any atom, we must add energy. It costs us energy to do that. The process is always endothermic. If we take an electron and we add it to an atom, then the process may be endothermic or it may be exothermic, and we learned that it's the electron configuration of that atom that helps us tell the difference. Now, overall, the formal charge is based on the idea that you want the atom in the molecule or the ion to have, as near as possible, the same number of electrons under its sway as it did as a free atom. In other words, we don't want to take away too many electrons or add too many electrons, because energetically that's a bad thing. And it interferes with the stability of the molecule. So the formal charge idea is to figure out how much movement there's been of electrons from each atom, from or to each atom. And that's why it's done this way. We start with the number of valence electrons the atom had, and then we have the idea that in the molecule or the ion, it owns its lone pairs, and it owns 1/2 of the valence shell bonding pairs, shared ones. Right? Now, if we do this right, electrons are conserved, and the formal charges must add up to the actual charge. If it's a molecule, the sum of the formal charges of all its atoms are 0, or is 0. And if it's an ion, they must sum up to the charge on the ion. And that's how we can check ourselves. Okay, I am going to go back to ozone for a minute. And I'm going to calculate for you the formal charges for the oxygen atoms on both of the resonance forms 1 and 2 here. Okay? First, I look at oxygen A here in structure 1. The formal charge of that oxygen, formal charge of oxygen A, is equal to the number of electrons oxygen came to the dance with, and that is how many? Valence? That's 6, isn't it? Minus the number of lone pair electrons that it has, and you see this oxygen is sporting 2 lone pairs here, so that's 4 electrons. And then minus half of the shared electrons, half of the bonding electrons. There are 4 because oxygen A is connected with a double bond, so this is 1/2 of 4. And so that's 6 minus 4 minus 2, it's 0. So we put above oxygen A 0 in parentheses here. And that helps us determine that's not a Coulombic charge, that's a formal charge. And they often are different. So we can apply that to each one of these. And I want you to look at this. Oxygen A has 0, and oxygen B has +1. Here's B, +1. Now notice here, something worth remembering, the sign comes before the number in formal charges. In real charges, it comes after. If this were the real charge, it would be 1+. That's how we communicate the difference. All right? And oxygen C has a -1 formal charge. Let's check ourselves. +1 and -1 is 0, and so our formal charges add up to 0, the charge we expect on a molecule. Now for B, it's switched around. Oxygen A has a formal charge of -1. Oxygen B has a formal charge of +1. And oxygen C has a formal charge of 0. Now you can see from this that both forms, both resonance forms, have the same set of formal charges. That means that they contribute exactly the same amount to the resonance hybrid, as we saw before. And talk to you about the rules of what is a good formal charge and what's not so good. There are 3 of these rules in order of sort of decreasing importance. If you do what we just did with the chloride ion, and you end up with more than one good Lewis dot structure. We'll do nitrous oxide in a few minutes, and you'll see it. Then you need to decide, based on formal charges, which ones are which one is the one that contributes most to the resonance hybrid and describes the molecule most directly. So the first step is we want a small formal charge, whether it's plus or minus, and those are always preferable to larger formal charges. Remember we said the formal charge, the magnitude of the formal charge tells a little bit about how many extra electrons an atom has in a molecule compared to the atom itself, or how many electrons it's lost in its state in the molecule compared to what it was as an atom. All that costs energy, and so we want to keep that to a minimum. So that's the first one. The second one is we want to avoid formal charges with the same signs on adjacent atoms. That is an indication of this Lewis dot structure being not as important to the real molecule as another might be. Okay? And the last one is the more negative formal charge should be on the more electronegative atom. Now that's not going to stick with you very long unless I do some examples. So I'm going to do the cyanate ion, which is the classic one that everybody does at this point. NCO, the cyanate ion, has actually 3 different Lewis dot structures that you can write for it, which have good octets. They are octet okays. and one of them has a triple bond between the carbon and oxygen and a single bond between the carbon and nitrogen. If you apply the rules, that will mean on nitrogen we have a formal charge of -2, on carbon 0, and on oxygen +1. And we check ourselves to be sure we did this right. -1 and -2 and +1 gives -1. So it looks like we assigned this probably correctly. Now the next Lewis dot structure has double bonds between carbon and oxygen and carbon and nitrogen. And when you do it that way, you get a -1 formal charge on the nitrogen and 0 on carbon and 0 on oxygen. That has all good octets, so we'll keep that one as well. The last one has a triple bond between the carbon and the nitrogen and a single bond between carbon and oxygen. Okay, if we do the formal charges, a 3-bonded nitrogen with a lone pair gives you a 0 formal charge. A 4-bonded carbon is always a 0 formal charge. And a single bonded oxygen is -1. So that looks like an acceptable one as well. All three of these are acceptable with respect to the octet rule. All right, so how do we choose between them? We use these rules up here. And we're looking for the smallest set of formal charges. What we'd like to have is all zeros if we could get it. In this case, we don't have any of them that have all zeros. So lacking that, then we want the numbers to be as close to 0, either plus or minus, as possible. And if we look at A, it is the least desirable using that criterion because it has a -2 and a +1 and a 0. So A is less important than either B or C because of the magnitudes of its formal charges. So we're assuming that this description of the cyanate ion is not a very good description, and that B and C are likely to be better. And if we want to compare B and C, since they are equal in the magnitudes of their formal charges, we have to go a little bit further down the list here. And 2 does not apply because the only things that are the same on adjacent atoms are zeros. So we don't worry about that. We go down to 3 and we look for a case where a more negative formal charge should be on a more negative atom. If you look at B and C, B has the negative charge on nitrogen and C has it on oxygen, and you all know oxygen is more electronegative than nitrogen. So C ought to be the most important resonance structure. These are all resonance forms. Should be the most important resonance structure, and it should describe the cyanate ion better than either one of these. What do I mean by that? Well, if you look at the characteristics of C, it says that the get the pen turned on here. The cyanate hybrid probably has, if you look at the two best of these, C is the best one. That's better than B. That's better than A. So B and C come closest to describing the hybrid, with C being the better of the two. So the hybrid would appear to have a carbon-nitrogen bond, and the bond order ought to be between 2 and 3, maybe closer to 3. So the carbon-nitrogen bond distance, for example, ought to be closer to a triple bond than it is a double bond. And likewise, if you look at the carbon-oxygen bond, the bond order should be between 1 and 2. And therefore, the bond length ought to be somewhere between the typical bond length from Chapter 9 for a carbon-oxygen single bond and a carbon-oxygen double bond, and probably it'll be a little closer to the single bond. So the formal charge gives us some real insight into the molecule. We make some pretty subtle and fairly sophisticated predictions about this ion, and they turn out to be right. I'll let you confirm it yourself, but we have a tool then that is fairly effective in predicting the characteristics of the hybrid. Where are the problem children of this particular story? And the problem children include cases where the center atom starts with too few electrons to ever get an octet in an ordinary molecule. And for example, if we look at the elements beryllium and boron here, they both form some covalent compounds, some molecules. Beryllium also forms ionic compounds, but boron doesn't. You could see that beryllium starts with 2 valence electrons and boron starts with 3. So beryllium's going to need to pick up 6, and boron would need to pick up 5 in order to get an octet. And the problem with that is there's no simple way to do it. If you look at 2 molecules based on beryllium, and one based on beryllium, one based on boron, beryllium forms in its molecules 2 bonds. So if you look at BeCl2, for example, that molecule, it has only 6 electrons around the beryllium. Only 4 electrons around the beryllium here. And boron has 6 electrons around itself in BF3. So neither one of these reach an octet. And so when that happens, your toolkit says, oh, I'll make a double bond from one of pairs of electrons on the outermost atoms. So if you do that, in the case of beryllium, you could make a double bond here, and you could make a double bond there. And that would give beryllium an octet. And in the case of boron, you could make a double bond by taking, say, that pair of electrons and make a double bond for BF. But if you do it, look what happens. Don't just stop there. Check it. The Lewis dot structure for this double bonded beryllium chloride monster here is the formal charges are very bad, and would suggest that this is not an important contributor to the hybrid for this particular molecule. And in fact, the experimental information bears that out. That this, you just simply don't find bond distances that are anything close to what would be a double bond. For boron, you can make a double bond very nicely, but again, look at the formal charges here. There's no formal charges up here, and now you get formal charges. You've got a -1 on the boron and a +1 on the fluorine. Well, the fluorine is furious with that. It needs the -1 because, of course, it is the most electronegative element that Pauling gave us. So neither one of these achieves an importance that would make it worthwhile to do these things. Satisfying the octet rule just doesn't lead us anywhere in terms of stability. So we call these kinds of molecules electron deficient molecules. The beryllium is electron deficient because it has only 4 electrons, and the boron has 6 electrons. And that happens typically when the central atom starts off with only 2 or 3 electrons. Okay? So, unfavorable formal charges make these much less important. Now, sometimes the presence of an electron-deficient molecule leads to the formation of what are called donor bonds. A donor bond between ammonia takes this lone pair on the nitrogen in NH3 and shares it with the boron here, which has 6 electrons and would dearly love to have 2 more. And so we get something that looks like this, a donor bond. A donor bond means that the pair of electrons that make up the bond both came from the same place, in this case, the nitrogen. Well, this is not perfect because it leads to formal charges that aren't zero, and this suggests this bond's not, enough to build a bridge on. But it does have some stability, a reasonable stability. If you heat up a molecule like this, however, it comes back apart. Then there are odd electron molecules, and these are easy to understand. If the total number of electrons in the valence for the atoms that are there is an odd number, something is not going to have an octet. Something will have an unpaired electron, and it may have 7 electrons. It can never have 9 if it's a carbon or a nitrogen or oxygen, something like that, but it can have 7. And when that is the case, when there's 1 or 2 or 3 electrons unpaired, these things are called free radicals. If we look at nitrogen dioxide, and you count the electrons, it's 5 plus 5 plus 2 times 6. 12 and 5 is what? 17 electrons. 17 electrons. And if you try to draw a Lewis dot structure, you can either do it with the lone electron on nitrogen, in which case you get something that looks like this, or the lone electron can be on oxygen and it looks like this. Now, when you have molecules that lack an octet, you can't put too much stock in the formal charges, because not having an octet is a much more serious problem than having one or the other of the formal charge combinations that we said told us how much that particular resonance form contributed. So when this is the case, all we can say is that some atom or atoms in the molecule will not have an octet, and that will make this maybe a very reactive molecule. For example, nitrogen dioxide, in its pure form, is a reddish-brown gas. Nasty stuff. It's in large part responsible for the orange color. When you see orange-colored smog over Los Angeles or someplace else, this is what's primarily responsible for it. If you took nitrogen dioxide and cooled it down, the electrons can pair up and form a bond, a single bond between the nitrogens here. This is not all that stable. I'll let you figure out why. As you heat it back up again, then some of the nitrogen dioxide can come back. Okay. The other end of the scale is expanded valence shells. Here, if you have a central atom that has Z greater than 12, what does that mean? Well, 12, this is magnesium. If you look at hydrogen, helium, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If you have it greater than 12, in other words, starting with aluminum, you can have an expanded octet, and this will allow the center atom to accommodate more than 8 electrons. And the reason that the valence bond model gives for this is that there are empty d orbitals in these atoms. For example, with aluminum, there are empty 3d orbitals that could be used to form more bonds. The argument against doing that is that those 3d orbitals are very high in energy, and because of that, they don't contribute much stability to this system. So there are some other, there is at least one other explanation. It's not much better than this, so I suggest we just stick with this. And look at some examples. Here's sulfur hexafluoride. Here's a molecule that's so stable. It's used in high voltage transformers to keep the system from arcing and having electrical lightning inside of it. Okay? I'll start again when you finish with your laptop up there. Is that a laptop? Would you close it, please? Thank you very much. And anybody else that has one, please close theirs too. Paper is much better. Okay, sulfur hexafluoride has a sulfur with 1, 2, 3, 4, 5, 6 bonds. 6 single bonds. And that means 2, 4, 6, 8, 10, 12 electrons around the sulfur. Well, that's okay because sulfur has a Z value which is greater than 12. So it can accommodate more than 8 electrons. So this is called an expanded valence shell. Another one, which is based on phosphorus, which is right beside sulfur, and also has the 12, greater than 12 Z value, is PCl5. PCl5 has 10 electrons around the phosphorus in this compound, and that is an expanded valence shell. Of course, phosphorus and chlorine also form PCl3, which obeys the octet. So in this case, it's expanded octet. And one little observation from yours truly is that this happens more frequently than not when the attached atom has a high electronegativity. Oxygen, fluorine, chlorine, sometimes nitrogen. That's where it happens the most. Okay, now you can obviously see that with SF6 and PF5 because there's 6 bonds, that's got to be 6 electrons, right? 6 electron pairs. But you can even have an expanded octet when the center atom only is bonded to 4 or even 3 other atoms. We look at sulfuric acid, and this is H2SO4. The center atom is sulfur, and when you do the Lewis dot structure, which you should be able to do, the hydrogens are on oxygens, not on the sulfur, and that leaves us with this Lewis dot structure, which is octet, okay. However, it has relatively large formal charges, +2. Question? +2 on the sulfur, -1s on the oxygen. So that is a octet satisfactory structure. However, the formal charges said the real molecule isn't probably going to look like that if there's another possibility. And the other possibility is that we make double bonds between the oxygen and the sulfur here and the oxygen and the sulfur here. That makes sulfur have 2 single bonds to oxygen and 2 double bonds to oxygen. And when you look at the formal charges, sure enough, you get all 0 formal charges doing it that way. And even though A and B are both valid resonance forms, the formal charge rules suggest that B is a better representation of sulfuric acid's molecule and the bonding in it than A is, even though sulfur has 4, 6, 8, 10, 12 electrons around it. There are 2 more bonds. And that's something I should stop and mention just a minute. If you form 2 more bonds, that stabilizes the molecule by approximately 2 bond energies, right? Whatever that might be. So in going in this direction, you not only get better formal charges, but you get better thermodynamic properties in the sense that if you added up all the bond energies here, they would be quite a bit more than over here. So presumably that means the delta H formation of this structure is greater than it would be for that structure, if you can think hypothetically about it at least. Well, if B contributes more to the hybrid because it has lower formal charges, then that should mean that the hybrid is going to have some sulfur-oxygen bond distances which are shorter than others. Whereas over here in A, all the sulfur-oxygen bond distances look like they're the same. Right? Well, if you look at the observed bond lengths for sulfuric acid, there are 2 of them, and these are the ones to sulfur to oxygen that has a hydrogen attached. They're 157 picometers long. And that's pretty close to a sulfur-oxygen single bond, if you look up a single bond in the table in Chapter 9. And then it has two that are 142 picometers, significantly shorter, and in the neighborhood of what you might expect for double bonds. So what experimental evidence there is seems to back up the formal charges here in this description.